Today we will discuss the introductory course on superconductivity, and this is the course for BTech first year as well as BSc first year students. So in this presentation I presented the superconductivity in a very simple way so that it can be understood easily, and it will take uh, 1 hour, roughly 1 hour. What is superconductor? Superconductivity is a phenomena in a certain material at extremely low temperatures characterized by exactly zero electrical resistance and exclusion of the interior magnetic field, that is Meissner effect. That means the exclusion of the interior magnetic field is called the Meissner effect. So the superconductor has two property. One is exactly zero electrical resistance and the exclusion of the interior magnetic field, or which is also called the Meissner effect. Here are some example of superconductor. The first one is lead, niobium nitride. The founder of superconductivity is Kamerlingh Onnes, and the phenomena was discovered in 1911 while Kamerlingh Onnes was studying the behavior of mercury by decreasing the temperature and plotting the electrical resistivity. He saw that the electrical resistance suddenly decreases to zero at a particular below a particular temperature. The particular temperature is called the transition temperature or the critical temperature. From this figure we see that in case of normal metals, as we decrease the temperature, the resistivity decreases, but it never goes to zero. But in case of superconductor, the resistivity decreases and suddenly it drops down to zero as we go below Tc. That particular temperature, Tc, is called the critical temperature. And for this discovery, the Kamerlingh Onnes was given Nobel Prize in Physics in 1930. As already I have discussed that critical temperature is the temperature below which the resistance of the material becomes zero. That means the normal conductor becomes superconductor. So here we can see that Tc is the critical temperature, and below this region represents superconductivity, and this region is for the normal conductor. So two main characteristic features of superconductors are zero electrical resistance and Meissner effect. Zero electrical resistance, as already discussed, that electrical resistance comes due to the collision of electrons. It comes due to collision of electrons with the collision of electrons with phonons. Phonons means lattice vibration. So as the super electrons does not collide with Superelectron does not collide with the lattice phonon. So in superconductor, the electrical resistance is zero. That means we have infinite conductivity. So electrons flow without facing any resistance. That's why we get no heat generation in the material. And the next effect is the Meissner effect. What is Meissner effect? When the superconductor is cooled below its critical transition temperature Tc is already discussed, all the magnetic flux are repelled by the superconductor. In the figure, we can see that these lines are the magnetic lines of force. Now in this case the superconductor is above Tc, that is the temperature of superconductor is above Tc, critical temperature. In this case, all the magnetic lines of force passes to the superconductor. But when we decrease the temperature below Tc, all the magnetic lines of force passes uh, cannot pass through the material. That means the superconductor expels the magnetic lines of force. This phenomena is called the Meissner effect. So as no magnetic lines of force passes through this superconductor, so magnetic field intensity B is zero within this superconductor. So here here B equals to zero. And also we know that for perfect diamagnetic material, magnetic susceptibility Km m by h equals to -1. So in case of superconductor, as it shows perfect diamagnetism, so Km will be -1 in this case. There are other important properties of superconductors such as effect of magnetic field, effect of impurity, flux quantization, entropy and coherence, specific heat, and Josephson effect. First, we will discuss about the effect of magnetic field. Similarly, as we previously discussed about the critical temperature, there is a particular temperature, particular magnetic field Hc, above which the uh, superconductor becomes normal, and below which it remains the superconductor. That means if we increase the magnetic field strength above Hc, above Hc, it will become a normal metal. That Hc is called the critical magnetic field, and it depends on temperature. And the expression of variation of Hc is given by this expression. Hc equals to h naught 1 minus t square by tc square, where Hc is the critical magnetic field at temperature T, H naught is the critical magnetic field at temperature 0. At Tc is the critical temperature, T is the temperature, any temperature T below Tc. So in this figure we can see that the shaded region is the superconducting state and the outer region is the normal state. So the expression is a parabola like structure, and we see that at t equals to 0 critical magnetic field is the maximum H naught, and when T equals to Tc, critical magnetic field is 0. So in the so here maximum critical magnetic field, and here minimum mean magnetic field. Isotope effect. According to Reynolds, the transition temperature of a superconductor material is proportional to 1 by root under m. That means as we increase the isotopic mass of a superconductor or impurities to a superconductor, its critical temperature decreases as we increase the isotopic mass of the superconductor. So Tcm to the Tc root m is equals to constant. Flux quantization. In this figure, this is a superconducting. This is a superconducting ring, and uh, if we apply the magnetic lines of magnetic field through this ring, the magnetic lines of force or the magnetic field becomes quantized while passing through this superconducting ring, and the quantized flux is given by phi equals to nh by 2e, where n is a integer 1 2 3 4, and h by 2a is a constant which is called flux wide, whose value is given by 2.07 into 10 to the minus 15 Weber in CGS unit. H is the Planck constant and E is the charge of an electron. So what is flux quantization? Flux quantization means when the magnetic fields of lines passes through a superconducting ring, the magnetic field becomes quantized. This phenomenon is called the flux quantization, and the quantum the and the quantum of flux is h by 2e, that is flux wide. Specific heat. As we know that for normal metal, the specific heat varies as At plus Btq. The first part is the electronic part and the second part is the lattice part. So in first case, the electronic part varies as proportional to T, and in the second case, the specific varies as T to the power Q, the third power of T. That is the temperature. In case of superconductor, the lattice part, uh, the lattice part do not get modified. Only the electronic part has contribution, and this first part get modified, but get modified as CST equals to constant multiplied by e to the minus delta by kt. That means it varies as the first part varies as e to the minus delta by kt. That means it varies as exponentially. And the delta is given by Eg by 2. It is called the energy gap parameter, where Eg is the band gap. Is the gap between the lowest excited state and the Fermi level in case of superconductor. So here we can see that as we in case of normal metal, The decrease in temperature results in the decrease in the specific heat, and there is a continuous decrease of the specific heat in case of normal metal. But in case of superconductor, there is a discontinuity and T equals to Tc. Suddenly, at T equals to Tc, suddenly the specific heat jumps to a higher value, and from there it decreases smoothly. Entropy and coherence. As we already know that entropy is a measure of orderness. The larger entropy means the lower order, and when the entropy is small, the system is more ordered. When the when the normal conductor becomes superconductor, the superconducting states become more ordered. That means its entropy significantly decreases. In this figure, you can see that in case of normal metal, the entropy is larger than the superconducting state at a particular temperature. That means the superconductor are more ordered state. Now, what is the coherence length? The electronic, this order may extend up to 1 micrometer. 1 micrometer 10 to the minus 6 meter. This order, the range of this order is called the coherence length. Now, types of superconductor. There are two types of superconductor, type 1 and type 2. This is the type 1 superconductor, and this is the plot of type 2 superconductor. This is the image curve of type 1 and type 2 superconductor. So, in case of type 1 superconductor, we have only two states. One is normal state and another is superconducting state. But in case of type 2 superconductor, we have three states. One is uh, superconducting state, then mixed state or vortex state, and then normal state. So in case of type 1 superconductor, we have only one critical magnetic field. But in case of type 2 superconductor, we have two critical magnetic field, Hc1 and Hc2. And the average magnetic field, that is Hc1 plus Hc2 by 2 is taken as the magnetic field of the critical magnetic field of the type 2 superconductor. In case of type 1 superconductor, the critical magnetic field is very low, but in case of type 2 superconductor, the critical magnetic field is large compared to the type 1 superconductor. This type 1 superconductor is also called the soft superconductor, as their critical magnetic field is small, and the type 2 superconductor is called the hard superconductor, as their critical magnetic field is large. So these are the properties of type 1 and type 2 superconductors. Normally type 1 superconductor are normally the pure superconductor, and in case of type 2 they are normally the compound materials. Josephson effect. What is the definition of Josephson effect? The tunneling of superconducting electrons through a thin insulator placed between two superconductors is known as Josephson effect. This effect is named after the British physicist Brian Josephson in 1962. In this figure, we see that we have two superconductor, one superconductor 1 and superconductor 2, and between this superconductor one thin insulator is placed where the width of the insulator is very of the order of 1 nanometer. This is also called Josephson junction. When this Josephson junction is of the order of 1 nanometer, uh, Cooper pair or electron pair can tunnel from one superconductor to another superconductor. This effect is called the Josephson effect. And what is the reason of this Josephson effect? This is due to the wave nature of electrons. The electrons can tunnel from one superconductor to another due to its quantum mechanical behavior. So there are two types of Josephson effect. One is DC Josephson effect and another is AC Josephson effect. And one thing we should know that the what are the Cooper pairs? Cooper pairs are the electron pairs. Cooper pairs are the electron pairs having opposite spin. That means two electrons having opposite spin can make a pair via a phonon. That is called the Cooper pair. So this is a Cooper pair. This is a Cooper pair. This Cooper pair can tunnel from one superconductor to another superconductor if the Josephson junction is a very small, is a very thin. That means of the order of 1 nanometer. DC Josephson. What is DC Josephson effect? DC Josephson effect is a direct current crossing the insulator in the absence of any external electromagnetic field. If we are not applying any voltage through this uh, through this system, that is uh, the we have two superconductor sandwiched between the insulator, and we are not applying any voltage, and in this case we measure the current, we will get some value, that is the DC Josephson effect. But in what is the AC Josephson effect? When we apply some voltage, here we applied some voltage V between the superconductors, and high frequency alternating current flows through the superconductor. The frequency of the AC current is V equals to 2eV by H. V is the applied voltage, E is the electronic charge, and H is the Planck constant. This effect is known as AC Josephson effect. That means in case of DC Josephson effect, no voltage is applied externally, and still we get some current. But in case of AC Josephson effect, we apply some voltage and we get a fluctuating or AC current of frequency 2eV by H, where V is the applied voltage. Superconducting quantum interference device, or SQUID. A SQUID is a very sensitive magnetometer used to measure extremely weak magnetic field. In this figure, we can see that we have two superconducting ring and two Josephson junction, and we have also applied some voltage V. This system is called the SQUID. The current flows from positive end to negative end. This Josephson this squid can be used to measure very small magnetic field as low as 10 to the minus 18 Tesla, 5 into 10 to the minus 18 Tesla. It can be used to measure biological kind in the human brain because the biological kind of the human brain is very small. So we can use squid, and also squid can be used to measure the Earth's magnetic field. London equations. The supercurrent density, that means the current which is flowing through the superconductor is the supercurrent density Js, and this current density Js follow a equation that is called the London equation. That means the supercurrent density Js of a superconductor is described by the London equation dGs by dt equals to ns e square E by m, where ns is the super electron density and E is the electric field. And if we write this equation in differential form, it will be curl of Js equals to minus ns E square B by m, where B is the magnetic field. So these both equations are known as London equations, which are the expressions of the supercurrent density within the superconductor. What is penetration depth? In this figure, we see that we have superconductor. This is the superconductor, and when we applied some magnetic field to this superconductor, the magnetic field comes to the surface and then decreases exponentially. The distance where the magnetic field at the surface becomes 1 by E to this 1 by E of its initial value, that is surface value, the distance is called the penetration depth or London penetration depth. This is the expression of magnetic field through the superconductor, that is Bx equals to B0 e to the minus x by lambda L, where Bx is the field at a distance x, B0 is the field at the surface, and lambda L is called the London penetration depth, whose expression is root under m by mu naught n E square. So m is the electronic mass, n is the electronic super electronic density is the electronic charge, and mu naught is the permeability of free space. So the distance where the field becomes 1 by E times of its initial value. That is, if we put x equals to lambda L, then Bx will be B0 by E. That is, at x equals to lambda L, that is at London penetration depth, the magnetic field becomes 1 by E of its surface value or initial value. BCS theory. BCS theory is the most successful attempt to explain the superconductivity. BCS, the name BCS comes from three scientists, Burdin, Cooper, and Schrieffer. And due to their this explanation of the superconducting behavior, they were awarded Nobel Prize. And this theory was given in 1957. According to them, the superconductivity is due to the attractive force between two electrons mediated by lattice quantum phonon. These two electrons is called the Cooper pair. We can see that these two electrons make a pair via a phonon. The distance between these two electrons is 100 nanometer. These two bounded electrons is called the Cooper pair. This electrons pair does not experience any resistance while traveling through the lattice. As these electrons or this electron pair or Cooper pair does not experience any resistance, so we have zero electrical resistance of the superconductor. What are the applications? The main application of superconductor is in producing large volume, stable and high intensity magnetic field, which can be used in MRI and NMR, nuclear magnetic resonance and magnetic resonance imaging. It can be used in high sensitivity particle detectors, in maglev trains. This is the best use of superconductor in maglev trains. This superconductor creates a repulsive magnetic field so that the train will float above the superconductor. This virtually eliminates the friction between the train and the track. So there are no friction between the train and the track, so the train feels no resistance and its speed becomes very high. There are other medical applications in NMR, nuclear magnetic resonance. In case of brain scanning, we can use NMR, brain wave activity to detect brain tumor and defective cells, also to separate damaged cells and superconducting solenoids, hydrodynamic power generation, plasma maintenance. In Large Hadron Collider or particle accelerators, superconductors are also used to make extremely powerful electromagnet to accelerate charged particles very fast.